Yeah, actually, I drank it. I'm almost done today. Okay, page 9. Pinky, if someone asked you the $1,000,000 question and asked you to state what a logarithm is, what would you say?
What? The inverse of exponential.
Yeah, it is the inverse of an exponential function. Yeah, if you ask the right person, I'm sure you would. That's right. A logarithm is the inverse of an exponential function. How do we get the inverse of any function? No, that's the reciprocal, not the inverse. Reflection over the line y equals x. That is true. Is that how we always found the graph of the inverse? Did we reflect it over the line y equals x? Is that what we do? No. What do we do? No, you switch x and y. Take points on the original graph, switch x and y, or switch y and x around, and that'll give you the points on the inverse, right? The domain of the function is the range of the inverse. The range of the function is the domain of the inverse. They are opposites of each other. So yes, switch x and y around. So again, we saw that a logarithmic function is the inverse of an exponential function. So this example says graph the inverse of an exponential function. So we're going to get a logarithmic function. Part A says state the inverse of f at x equals 3 to the x. Now, the first thing we always did when we wanted to get the equation of the inverse is if it was in the form f at x equals, we put it in the form y equals. All that singing must have fouled it up.
He's not here. It's probably in his cupboard.
The answer is yes. No. Yes. That's was that 11?
We're getting 11.
What if something actually happened?
Yeah, what if someone's in danger?
They're like panicking, trying to like put the right.
Yeah, we're supposed to save them.
And you're keep saying
Not
test
doing
it.
That's what people in lessons are.
I assume so. Yeah.
Okay, there we go. So instead of f at x equals, we write it as y equals. So what's the next step then to write the equation of the inverse? Do you remember, Chloe? What's the next step if you want to write the equation of the inverse? We haven't done that yet, though, right? All we did is replace the f at x with y, and then, yes, you swap x and y. But normally we put it in its original form, which is in the form y equals. So we need to get y by itself here. And this is where we will use logarithms. Because we don't have an algebraic step that you've learned in previous math courses where you can get the y, which is a power by itself. This is where we use logarithms. So we are going to convert from exponential to logarithmic. Samantha, I love your shirt. I'm a fan. I'm sorry? Okay, well, tell your sister I like her choice in music. I went to Graceland. I saw where Elvis lived. I really, yeah. Pretty cool. Didn't see where he slept. You couldn't go to his bedrooms, but got to see the rest of the house. Okay, so we're going to convert this from exponential function to logarithmic function. So remember how we do that? The bases are the same. The base of the exponential function will be the same as the base of the logarithmic function. So this will be a log with a base 3. We get the remaining parts, remember, by cycling, starting with the base and cycling through. When you do that, it tells you the order the other pieces are written. So after the 3, which is the base of the log, you're going to get the x. And after that, That's going to equal the y. So now we've got the equation of the inverse. We've got y by itself. So it didn't really do an algebraic step there, but we just converted from exponential form to logarithmic form. So we've stated the inverse of f at x equals 3 to the x. There's the answer to part A. Now we want to graph it. We're going to sketch the graph of the inverse and identify the following characteristics. So to sketch the graph of the inverse, I would start with points on the original graph. I'm going to get points on the graph of y equals 3 to the power x. That's our original function. If x is negative 2, again, I'm graphing y equals 3 to the x, or not graphing it by getting a table of values. When x is negative 2, y will be 3 to the negative 2, or 1 over 3 squared, or 1 over 9. When x is negative 1, 3 to the negative 1 will be 1 over 3 to the positive 1, or 1/3. When x is 0, anything to the power of 0 is 1. 3 to the 1 is 3. 3 squared is 9. So these are points on y equals 3 to the x. So this is for y equals 3 to the x. And I did this because now if I want to get points on the inverse, which will be log base 3 of x, right now the only way I can really do that is by taking this table and switching the x and y values around. We haven't really talked about evaluating logs with bases other than 10. Remember, if there is no base indicated, that means it's a common log base 10, and your calculator is programmed to evaluate logs with base 10 when you hit the log key. But we don't have this as a log with a base of 10. It's log base 3. So we will take the points on the original graph and we will switch them around. So these are the points that will be on that log function. The 0.19 comma negative 2. The 0.13 comma negative 1. The 0.1 comma 0. 3 comma 1 and 9 comma 2. In this case, the y-axis is an asymptote. The further that this graph goes down, the closer it'll get to the y-axis, but it'll never actually touch it. It is an asymptote. So there's the graph of that logarithmic function. The domain of this will be from 0, which is not included. That's why we use round brackets, to positive infinity. Right? The y-axis is a vertical asymptote. That's the domain. And let's write that. Actually, the range will be all real numbers. It'll go downwards forever and upwards forever. There is an x-intercept, and we found it in our table of values. That is the 0.1 comma 0. But there is no y-intercept because the y-axis is vertical asymptote. And we want to write the equation of that. That is the line x equals 0. It's an equation, so you got to have a variable. You got to have an equal sign. Okay. So this next one is the same type. We're asked to write the inverse of 1/2 to the power x. F at x equals 1/2 to the power x. And our first step in this case, again, is to change the f at x to the letter y. So, Juris, what's our first step to write the equation of the inverse? Switch x and y. Or if your name is Sant, you'll say switch y and x. And normally we get y by itself, but we can't algebraically get y by itself. So we'll do this by converting from exponential to logarithmic. So what will that look like, Ruhita? If I want to convert from exponential to logarithmic, what will that look like?
X over y is.
Convert from exponential to logarithmic. Remember, the bases are the same in each form. This logarithmic function has a base of a half, so when you write it as a log, it'll be log base a half. And to get the order that the other pieces go in, we start with the base and we cycle through. After the base half will come the x, so it's log base a half of x, and after that will come the y. So we converted from exponential to logarithmic, and this gives us the equation of the inverse of the original exponential function with y by itself, log base a half of x. So again, to graph this, which is what part B wants us to do, we'll start with a table of values for y equals a half to the power x. And we will choose some values of x, find out what y is, and then we'll use this to get points on the graph of the inverse. When x is negative 2, y will be 1/2 to the negative 2, which is 2 over 1 to the positive 2, which is positive 4. When x is negative 1, y will be 1/2 to the negative 1, which will be 2 over 1 to the positive 1. When x is 0, anything to the power 0 is 1. When x is 1, a half to the 1 is a half. And when x is 2, 1/2 all squared is 1/4. Because the base is between 0 and 1, this gives us a decreasing function. We've got the point negative 2 comma 4, negative 1 comma 2, 0 comma 1, 1 comma a half, and 2 comma a quarter. This is the graph of the original function, the exponential function. The x-axis is an asymptote. But we want to graph the logarithmic function. If we want to graph y equals log base a half of x, how do we do that, MJ? Flip the x and y values around. Why? Why can we do that? Yeah. Why are we doing that? Because it's an inverse, that's right. This logarithmic function is the inverse of the exponential function. That's why we can switch the x and y values around. Because the two are inverses of each other. So I've got the point 4 comma negative 2, 2 comma negative 1, 1 comma 0, 1/2 comma 1, and 1/4 comma 2. Again, this is a decreasing function because the original is also a decreasing function. So that's what the graph of the inverse will look like, the graph of that logarithmic function. Again, the y-axis is an asymptote. So if we state the domain of this, again, it'll be from 0, which is not included, to positive infinity. The range is from negative infinity to positive infinity. The x-intercept, it does exist. Again, it is the point 1 comma 0, but there is no y-intercept. The y-axis is a vertical asymptote. And its equation is the line x equals 0. Again, it's an equation, so we have to have a variable, and we have to have an equal sign in it. So again, this is all possible because we know that to get the graph of a logarithmic function, we can graph the inverse of it, which is the exponential function, or vice versa. We have yet to learn about how we deal with logs with bases other than 10. Okay? So without using technology, estimate the value of log base 2 of 14. Without using technology, estimate. And then we'll see how we can maybe use some technology to figure out what that value is. So we can do it by, again, letting log base 2 of 14 equal x. We want to know what it equals, so let's let it equal the variable. If we write that in exponential form, Earl, what would that look like? In exponential form. Can you help him, Moyen? Can you help him? He's trying to write that in exponential form. What would that look like? Don't tell me to wait, young lady. I'm in charge here. Take your time. Talk yourself through it. Phone a friend.
Okay, 14.
What's the key word that we always say, the key phrase when we're converting? Start with the base and don't work your way through, you cycle through.
It's the same thing.
No, it's not.
Yes, it is.
Don't argue with me.
Hmm?
I don't know. I'll play your silly game. Would it be?
I think that's.
Yes. Start with the base and cycle through. Remember that the base of the log will be the base in the exponential form. So you start with that number. That's your base. We're trying to estimate what the value of x is because x is the value of log base 2 of 14. We just changed it from logarithmic to exponential. This is asking 2 to the what power is 14. So you should realize that's going to be a irrational number, I should say. We know that 2 to the 4th is 16. 2 cubed is 8. So 14 is between 8 and 16, closer to 16 than it is to 8. So our answer for x would be closer to 4 than it would be to 3. So maybe 2.38 or something like that. It's an estimate, right? It is an estimate. 3.8 is what I said was our estimate. Between 3 and 4, closer to 4 than it is to 3, because 14 is closer to 16 than it is to 8. So we can use our calculator to confirm our guess. If you went 2 to the power 3.8, so that's pretty close to 14. You might remember we saw before that we could use our graphing calculator to find out a more accurate estimate by graphing. Graphing 2 to the power x as our first equation. And then y equals 14 as our second equation. So when we look at our windows, our y value needs to be at least 14. So we can see that second line. So let's set it to 15 and maybe a scale of 2 on the y-axis. So when you graph it, there's your exponential function. There is the line y equals 14. We can find the point of intersection. So it's 3.807. So again, we estimated 3.8. There's a more accurate estimate. And it's an estimate because that number needs to be rounded. So approximately 3.807. a little more accurate of an estimate. But okay. So either way, you need to first convert it from logarithmic to exponential. So log base 3 of 50, well, that will have to be between 3 and 4. Because log base 3 of 50 really means 3 to what power is 50? And the reason we know that is because if you take log base 3 of 50 and you set it equal to x, and then you want to convert from logarithmic to exponential, what would that look like, Brett? Is that right, Jonathan? Yes. Start with the base and cycle through. The bases are the same in both forms. So again, 3 cubed is 27, 3 to the 4th is 81. This answer will be somewhere between 3 and 4, right? Maybe closer to 3.5 in this case. You could definitely check that on the calculator a couple different ways. 3 to the power 3.5. Okay, so we know that we're a little bit low. Maybe we try 3 to the power 3.6. That's maybe a little bit closer. Maybe 3 to the power 3.55. Closer. Yeah. And you can do that guess and check. Or, like we've seen, you can also use a graphing calculator. You can say y equals 3 to the x as our first equation. Our second equation will now be y equals 50. When we set our windows, our y max will have to be something larger than 50. Let's say 55. And I'll set my y scale to 5. And you need to find the point of intersection. So yeah, it looks like 3.56 is the best estimate. 3.561 if we want. Okay, that's fine. So it would be 3.6. All right. So we mentioned at the start that one of the applications of logarithms is to compare intensities of earthquakes. We also see that we can use logarithms to compare items that are on the pH scale. So in 1935, the American seismologist Charles Richter developed the scale formula for measuring the magnitude of earthquakes, and they call it the Richter scale, or the Richter magnitude. M of an earthquake is defined as M equals log of A over A sub 0, where A is the amplitude of the ground motion, usually in microns, measured by a sensitive seismometer. A sub 0 is the amplitude corrected for the distance to the actual earthquake that would be expected for a standard earthquake. In 1946, an earthquake struck Vancouver Island off the coast of BC at an amplitude that was 10 to the 7.3 times A sub 0. What was the earthquake's magnitude on the Richter scale? So we are told that M, the magnitude, can be written as a logarithm. It is the log of A over A sub 0. And we were told in this case that the amplitude, which is what A is, was 10 to the power 7.3 times A sub 0. So A, the amplitude, is 10 to the power 7.3 times A sub 0. The original formula has a denominator of A sub 0, so those two would cancel. And we would have the log of 10 to the power 7.3. Now, there is no base indicated for this log, right? the log, the argument, what you're taking the log of, is a power. And that power has a base of 10. But that base of the log, because it's not written, would mean that it's also 10. Whenever the base isn't indicated, that means it's a common log, which means base 10, which means you can use your calculator because it's programmed to evaluate common logs. So you just have to hit the log key, and we have the log of 10 to the power 7.3, which actually is 7.3. And it's not a coincidence that the answer works out to be the actual exponent. And we will see why fairly soon here when we start talking about laws of logarithms. But for now, we use our calculator, and the calculator gives us the answer. So that would be the magnitude of that earthquake, a magnitude of 7.3. Part B says the strongest recorded earthquake in Canada struck Haida Gwaii. So it used to be Queen Charlotte Islands. It's now called Haida Gwaii. It's also off the coast of British Columbia. It's north of Vancouver Island. It's kind of straight west of Prince Rupert, where Vancouver Island is obviously straight west of Vancouver. So it's further north. But anyways, this happened in 1949. It had a Richter reading of 8.1. How many times as great as A sub 0 was its amplitude? Okay, so again, we'll use that same format equation, that m, the magnitude, is log of A over A sub 0. And we are told that this earthquake had a Richter reading, which is its magnitude of 8.1. So 8.1 equals log of A over A sub 0. We want to know, once again, how many times as great as A sub 0 was its amplitude, which means we want to get A, the amplitude by itself. We'll get A, the amplitude by itself, and it'll be something multiplied by A sub 0, which is what we're looking for. How many times as great as A sub 0 was its amplitude? So again, we want to get A, the amplitude by itself. Now, to do this, again, this is a log. It's the log of A over A sub 0. And there's no base indicated, which again means that it is base 10. To get A by itself, again, we are going to convert from logarithmic to exponential. What would that look like, Sant, if we convert that equation from logarithmic to exponential? What would that look like? Samantha, what would Elvis say?
I think he would say 10 to 10.
And how are you getting that?
A base versus base, and then around.
Start with the base and cycle through. The base of the log is 10, so in exponential format, it will be 10 to some power. And again, when you cycle through, it tells you what order the other pieces are written in. So the 10 is the base. After the base is going to be an exponent. After the 10 comes our 8.1. So it's 10 to the power 8.1 equals A over A sub 0. And we want to get A by itself. And we would do that by multiplying both sides by A sub 0. So A will equal A sub 0 times 10 to the power 8.1. Or 10 to the power 8.1 times A sub 0. There's our answer. How many times more intense is A compared to A sub 0? Ten to the power 8.1 times as intense. That's right. So you could use your calculator to get that as an actual number. So that's a pretty big number. 125,892,541 approximately. Okay. Part C. Compare the seismic shaking of the 1945 Haida Gwaii earthquake with that of the earthquake that struck off Vancouver Island in 1946. So we want to compare them. We're going to see how many times more intense one is compared to the other. And we would do that by using division, right? If you want to compare, let's say, two student IQs, you take one IQ and divide it by the other, and that would tell you how many times more intelligent one student is compared to the other. Not going to mention any names here. But you're going to use division. So we will use the amplitude of the Haida Gwaii quake, because it is the one that was more intense, and divide it by the amplitude of the Vancouver Island quake. The Haida Gwaii quake has an amplitude, or a magnitude I should say, of 10 to the power 8.1. Whereas the one that struck Vancouver Island was 10 to the power 7.3. Now, I say 10 to the power 8.1. Again, it's actually the amplitude. So if you take this expression up here that I am drawing a shape around, if you want to get A by itself, we did that here. We multiplied both sides by A sub 0. So the amplitude of that earthquake is actually A sub 0 times 10 to the power 8.1. Pardon me? That's right, because the amplitude of the Vancouver Island will also be involving A sub 0. It'll be 10 to the power 7.3 times A sub 0. And yes, the A sub 0s will cancel. And now you're actually just dividing two powers with the same base. The law says you subtract the exponents and keep the base the same. It'll be 10 to the power 0.8. When you subtract 8.1 minus 7.3, that's where the 0.8 comes from. So that's approximately 6.3 times as intense. Okay? The largest measured earthquake struck Chile in 1960. It measured 9.5 on the Richter scale. How many times as great was the seismic shaking of the Chilean earthquake than the Haida Gwaii earthquake, which measured 8.1 on the Richter scale? So again, we could do this by dividing the amplitude of the Chilean quake and divide by the amplitude of the Haida Gwaii quake. So because the Chilean quake measured 9.5 on the Richter scale, its amplitude would be 10 to the power 9.5 times A sub 0. And that's divided by the Haida Gwaii quake, which is 10 to the power 8.1 times A sub 0. Again, the A sub 0's cancel. To divide those, we're dividing powers with the same base, we subtract the exponents, keep the base the same. That'll be 10 to the power 1.4 times as intense. And 10 to the power 1.4 is approximately 25.1 times as intense. Okay? So you can work on page 380 to 381, questions 8, 9, 14, and 21. I will put those solutions on Google Classroom so you can check your answers. Yeah.